hope you are doing very, very well. Just want to quickly make this video on this brief machine learning tutorial. So this is work that I did earlier on a dataset, on a notoriously difficult dataset called the fuel economy dataset. And if we just quickly look at the data, there's only 14 codes, right? That's because the data set is very large, it's very messy, and it requires a lot of cleaning and a lot of EDA to tease out some interesting relationships or behaviors. And a lot of people are not, they're not prepared to do that if the data isn't well behaved. So I took this as a challenge and actually went through it myself. Its counterpart is the Auto MPG dataset, which is a lot cleaner. And as you can see here, there's 228 codes. So at least 228 people have gone through this dataset and added it to their personal portfolios or personal projects and shared their code for education or inspiration. Not so with the fuel economy dataset. You will soon learn that with anything in data analysis, machine learning, making neural networks, whatever the case may be, most of your work and most of your time and effort will be in cleaning the data and doing some EDA, right? So step number one is to make your standard imports. Now the standard packages for thorough data analysis are generally pandas, numpy, seaborn and matplotlib for visualization, pandas for data frames, the actual data analysis, numpy for operations, matrices, arrays, some statistics, and if you're doing a lot of scientific works, you can add scipy in there as well. I've added this import in here because I don't like red writing and I don't like warnings, so I added that in there, right? So I have my fuel economy dataset saved as a CSV file on my desktop, and this Jupyter notebook is opened on my desktop, so all I have to do is just do a // and that's basically the root folder desktop that allows me to call in or read in the fuel economy database using pandas read CSV function. Okay, so .head enables us to look at the first 5 rows, and as you can see here, there are 3 dots in the middle. This shows that there are a lot more rows that the IDE, the Jupyter notebook, was not able to show. And if you look at the prompt here, there's 81 columns. That's a lot of data. A lot of data is not necessarily a good thing. Most of the time, it's a bad thing. Why? Because when you are doing data analysis, right, or when you are making a machine learning model, whatever the case may be, your job is to write a chapter, right? So we are all writing a book, or we are all part of the novel writing process, right? We cannot write the entire novel. We have to write just a chapter. If we try to write the entire novel at once, we will get lost, we will over-engineer, our results will not be good. Our job is to tell part of the novel, a good chapter, and then if we want to extend the data down the line and tell a new chapter, that is what we do. 81 columns is too much. My first goal is to decide which columns I need to answer my research questions and cut out all the rest. So step 3, ask some research questions. I focused on these 2. Can we predict the MPG, so that's the miles per gallon, or CO2 emission of a car based on the features here, based on the chosen features? And are there noticeable differences in where a car comes from? So I saw a lot of cars in the data set which were familiar to me, cars that came from the USA, cars that came from Germany, and cars that came from Japan. And I decided to ask the research question whether or not we can predict a car comes from USA, Germany, or Japan based on the features. So this means that we can narrow down the data set and only keep the columns relating to standard engine information, fuel cost, MPG, and perhaps greenhouse gas grade or greenhouse gas score, right? So another issue that a lot of people have when they try and do data analysis is the lack of domain knowledge, right? So I don't build cars, neither have I worked in a car factory. So I lack the domain knowledge to fully understand all of this data. That doesn't have to be the end. I ask the research questions which I know I can answer, and I choose the data set. I choose the columns that I know feeds towards the research questions that I'm trying to answer. And if there's any one column that I don't understand, again, it is your job as a data analyst, data scientist to do the research, right? So if you don't know what engine displacement is, you go and look it up. If you don't know what drive is, or you don't know the kind of drives to expect, you go and look it up. What is the difference between a forward drive, a rear wheel drive, an all-wheel drive, so on and so forth, okay? So I decided to keep these columns and basically make a slice of a data frame called keep columns, and I basically made a new data frame called fuel_1 that only keeps the chosen columns of the main fuel data frame. I look at the first 5 rows again, and our data is a lot tighter, okay? Now here's the big part. We need to start cleaning up the data. As you can see from the slice, there are a lot of missing values here. And there are a lot of values that are polluting our data frame. For example, if I care about the fuel efficiency of a car, whether that's to do with the greenhouse gas emissions or the miles per gallon, realistically, I don't want any electric vehicles in my data set because they will skew my machine learning algorithm, okay? Because they don't have any emissions, and the data does not include the emissions that electric cars make by getting power off the grid, because electric cars charge off the grid, so they do release greenhouse gases by proxy, but the data is not here, so we can't guess that, we can't predict it, so we should just remove it. Three types of fuel columns, we don't need that, so we should choose one fuel type column that will give us a very general and very understandable description of the vehicles. And also, just ahead, we also need to worry about columns that correlate too much with each other, right? So columns that correlate too much with each other skew the data because they basically say the same thing. And this is called multicollinearity. I can already guess that I'm probably going to have to drop, I've done this already, but I'm probably going to have to drop fuel economy score or GHG score because they pretty much say the same thing. If we want USA, Germany, Japan, then rather than choose every single vehicle from USA, Germany, and Japan, I'm just going to choose the top 4 manufacturers of each country and then remove everything else. Again, lots of data isn't always a good thing, okay? You should narrow down your data so that you can tell a good story, okay? Not have lots of data that tells a very vague story, okay? We also need to bear in mind which columns are categorical and which columns are numerical. If categorical and we're doing regression, then we need to encode those categorical columns. If the columns are numerical, then we need to scale the columns so that they will fit into our regression algorithms. Obvious stuff like any cars without a drive, remove, because we can't guess the drive of a car. I don't have the domain knowledge of Alfa Romeos to know whether a mini compact version of it will have a rear wheel drive, forward drive, or a 2-seater will have an all-wheel drive, vice versa. I don't have any domain knowledge. So rather than guess, remove. As I said, remove the electric vehicles, and we may do a pass at the end to remove repeats if it seems that some of the columns are repeats of themselves. Okay, so that is the plan. So as you can see here, I first looked at fuel type and I looked at each of the columns, and I judged that fuel type 2 was useless to us because there were a lot of missing values, and fuel type number 1, the first column, is also bad for us because there are too many values. So when we encode this, we're going to have a lot of different categories, and that's not a good thing. So I chose to stick with fuel type number 1 and drop the rest. In the middle of this, I decided to look at the correlation of the numerical values in the data frame using this correlation function. And using seaborn.heatmap, I'm able to see how the different numerical features correlate with each other. Highly positive values mean positive correlation, so as one goes up, the other also goes up as well. Negative correlations mean that as one goes up, the other goes down. So it's a it's a downwards slope. Now, if I care about MPG, then I want to look at what MPG correlates with, and as we can see, it combined MPG correlates inversely with engine cylinders and engine displacement and annual fuel cost, which kind of makes sense. So the higher the fuel cost, then generally the lower the miles per gallon. It's a gas guzzler, right? Also, tailpipe CO2 in grams. So the more CO2 emissions, then the likelihood is that the car is not going to be very efficient. And then there's some soft positive correlation with fuel economy and GHG score. Notice how fuel economy and GHG score are correlating perfectly with each other. So I eventually made a decision to remove GHG score. Okay. Just to have a look at engine displacement and engine cylinders, just to see what they look like, because again, domain knowledge or lack of it is key here. And I'm also noticing that they are pretty highly correlated with each other. So I'm trying to make a judgment whether, if they have the same shape, whether to keep one and throw away the other or not. Because engine cylinders looks very, very categorical, I decide to keep both. Okay, engine displacement looks a lot more continuous, whereas engine cylinders is kind of discrete, so I decide to keep both. Also, basing my next few tasks off of this third bullet point here, I make a slice where I'm only keeping the top 4 manufacturers of each country. So for Japan, I'm keeping Toyota, Mitsubishi, Nissan and Honda. For Germany, BMW, Volkswagen, Audi, etc., etc. And for America, Dodge, Ford, GMC, and Jeep. So that's basically this line of code here means that I'm just keeping the location where the make equals these specific values. This is called masking. And then I'm dropping the 2 fuel type columns that I said that I didn't want. Okay, so now I'm just checking the value counts, just making sure that I have a good selection of data. And then, because I said earlier that I didn't want any electric vehicles, I also drop any rows which have the fuel type 1 equaling to electricity. I also drop fuel economy score as well. Okay. So now I check the info again, and out of a previous max 38,000 rows of data, I'm now left with 18,000 rows of data with some missing columns. Eventually, I'm going to drop these because, like I said, I cannot guess what the drive of a vehicle is, right? This is just some line of code to change the engine cylinders to integer because they were floating before, which did not make sense since they are categorical values. I do a little bit of encoding, so in order to begin to form correlations between the country of a vehicle and its other features, I encode the American cars to 0, the German cars to 1, and anything else, Japan, to 2, right? So I make a new column or a new series called country, and I basically apply this mapping function to the make series, which gives me the country series. And as you can see, I have a decently healthy number of different vehicles from different countries, right? Now, if we look at the drive column, right, because we need to assess how, we need to assess what to do here. If you've got missing values, you don't immediately drop them. You still need to look at the column and see what's inside before you come to any conclusions. Okay, so what I've done here is that I've checked the value count, and I noticed that I've got rear wheel drive, I've got front wheel drive, I've got 4-wheel or all-wheel drive, but then I've got all-wheel drive, and I've also got 4-wheel drive. By and large, 4-wheel drive and all-wheel drive and 4-wheel drive or all-wheel drive are the same thing. I should probably add those columns together. And then with part-time four-wheel drive, I have no domain knowledge of what that is. I wouldn't know which column to put that in. And two-wheel drive, the problem with this one is that in two-wheel drive, I don't know which ones are rear wheel and which ones are front wheel. So amongst the mission values, not only do I need to drop those ones, I probably need to drop two-wheel drive and part-time. So I make a function with a bunch of if statements, basically passing the data, and if it's four-wheel drive or all-wheel drive, then I apply it to four-wheel drive. If it's all-wheel drive, I return four-wheel drive. So I'm changing the category of the data, and anything else return, and then I drop the rest, right? So again, you've seen this come up a bunch of times now, fuel.lock. So I'm basically looking at the locations, the rows, and putting mask in, and doing a sort of Boolean mask to decide what to keep and what to drop, right? And at the end, my drive column is now a lot more tidier and has a good number of rear wheel drive, front wheel drive, and four wheel drive. I want to know whether there are significant differences in a car's MPG or fuel economy if they are rear wheel, front wheel, or four wheel. I can already imagine that. I looked at this. Front wheel drive generally have better fuel economy because the axis, the drive axis is directly underneath the engine, right? So when the torque doesn't. Okay, I'm a physicist, but I'm not going to over-explain. Because the engine is directly on the wheels, it doesn't need to do a lot of work to carry the engine along with it. But rear-wheel drives, they have to turn a lot more because the engine is all the way at the far end of the vehicle. So the weight distribution is not there. So a lot more fuel is burned when you rev a rear-wheel drive car. Okay, so I've cleaned up the columns for the most part. Now, step number 5, we do some exploratory data analysis. Now, unless I have a good domain knowledge of the data, I don't always concentrate on describe because it can lead you to the bad habit of trying to make conclusions about the data before you've even visualized it. So I try not to pay too much attention to this until I've actually looked at the data. Just making a bunch of plots here. So as you can see, I'm just plotting. I'm categorizing by country and just looking at the annual fuel costs, the MPGs, and some of the engine data. You can already see here that Japanese cars have generally better MPG than the other countries, with America being the worst, Germany being middling, and Japanese being very good. Annual fuel costs are a lot less differentiated. However, tailpipe CO2, remember, there was a strong negative correlation between combined MPG and tailpipe CO2. So where America was the lowest MPG, it makes sense for it to be the highest in tailpipe CO2 emission. Okay, and some interesting data here where American cars have the highest engine displacement, whereas Japanese cars have the lowest engine displacement.